what I am going to do now is look at the problem of the FFT. So what we have over here is that there is a computation that is being performed. It is essentially some summation that you need to perform over here, right? And if there are n input values, those are then converted to n outputs, and the values themselves are complex valued floating point numbers in general. As part of assignment 3, we also went through the process of converting this into the AP fixed format, where you essentially had to use some fixed point representation, a finite number of bits with some bits reserved for the integer portion and the other bits reserved for the fractional portion. Okay, so all of these steps are already completed. Now the question becomes, how does that C code that you have written get converted into hardware? That is the first thing that we want to understand. The second is, once I have converted into hardware, how do I actually use it in a computation? Okay. So one thing that we need to understand to sort of get the overall picture of what we are trying to do over here is, the specific approach that we are following over here is that we want to implement accelerators for certain types of computations. Okay. This is not the only way in which HLS or indeed hardware synthesis is used, right. What you might do is that you actually have an arbitrary system where, for example, you have some inputs coming from an ADC going through your hardware module and going out through a digital to analog converter, where this and this are what we broadly call the outside world, right. So the ADC and DAC are essentially the interfaces to the outside world. The hardware module exactly gets the inputs that it needs per sample and then processes it in some way. The other way of doing it is, you have data available in some way, either from an A to D converter or already stored somewhere on a file. This goes into some kind of a processing system, right, and finally goes back to a data store. So we will call these data stores in general. It is some place where the data can be stored in some format that can be read and then written. In the simplest thing, that is just the same as an ADC, right. So over here what we want to do is essentially take this and partition it so that some part of it becomes hardware and the rest is running in software. Okay. So a term that you are likely to come across in the literature relating to this is essentially something that says hardware software co-design, or another word is partitioning. In fact, what we will be looking at specifically in the context of this example is the problem of partitioning. We have code that is already available in software. We want to partition it so that some part of it runs in hardware. The sort of subsequent step after this would actually be to do a hardware software co-design. And what co-design basically means is, as you are writing the software, you write it in such a way that it is able to make use of hardware facilities that are available to you, and also you create hardware that makes it even easier for you to write the software in a better manner. Okay. So it becomes an iterative process. You first come up with an idea for hardware, you use that in order to write the software, you get ideas on where the bottlenecks are, you then use that to further improve the hardware and so on. Okay. So the overall hardware software co-design problem is a very generic and very broad design problem, hard to solve in the general case. Partitioning is a bit more specific. You start out with a C code or a software code and then decide what parts of it are slow and how do you speed them up. That is the approach we are going to take here. Okay. So since we have already gone through the process of writing code for an FFT, I am going to straight away jump to the process of what does the FFT code look like, what happens when you run it through the high level synthesis tool, and try and understand a little bit about the outputs coming out of that tool. Okay. So here I have a piece of code which the TAs would have shared with you the other day, or you would have at least seen this code. Hopefully it is in any case familiar to all of you in terms of how you would have written your own FFT code. This is the test bench, very similar to the test benches that we used earlier in the automated test cases, right. There are two files, the input and the output, and what we do over there is read in all the values from the input into an array called data underscore in, call this function FFT, which takes data underscore in and generates a data underscore out, and then dump that value out, whatever was created, into well, or rather read in the value from the expected output and do a comparison to check whether the data, we are calling it data underscore MATLAB because it was generated from MATLAB and is sort of a reference code. It would probably be better to call it a data underscore ref as a reference code. If you find that for any one of the samples the difference over here exceeds some tolerance that we set, we basically make result equal to 1 and return result. Okay. Like I said earlier, this is a self-checking test bench. The input as well as the expected output are available to the test bench. Okay. So, all that it does is it runs the function FFT, computes data underscore out, compares it against the expected output, and if there is a difference it flags it. Okay. Now, this part over here where we return result is actually quite interesting and useful. Vivado HLS is able to make use of that in order to also check whether, not just to tell you whether or not your test data passed or failed, but it can use it one step further. Once you have got something that passes in C simulation, it can use the same test bench and test the hardware that it generates as well. Okay. And the way that it does is it relies on this return value. As long as the return value is something that will be 0 when it works correctly and non-zero when it fails, the self-checking test bench can essentially create some Verilog infrastructure which allows this part, the FFT function that you have over here, which right now is just a function called in C, it will convert that into something which will actually take the values in data in, pump them into the hardware one cycle at a time, wait until the computation has completed, read the data back and put it back into the array data underscore out, so that the rest of the program, the test bench, can continue in C. Okay. The function itself looks like this, right. The important part is pretty much just these 5 stages, right. So, if you think about it, what is happening over here is we have a 32 point FFT. Okay. So, there are 32 values out here, right, 0, 1, 2 up to 31 complex values. Okay. And the computations that happen are essentially, there is some kind of cross computation involving some twiddle factors, right, the exponent of minus j2 pi k n by n. What we can do is, rather than worrying about all of those computations, we just pretty much say, look, I am just going to assume that all of these inputs are fed into one block. I call this block as some core FFT 0, okay, with some parameters. I will call this stage 0. This will again generate another 32 outputs, which I can feed into another block, which would be my stage 1, right. Similarly, stage 2, stage 3 until I get to stage 4 and I get 32 outputs over here, right. Because I have 32 point FFT, the number of stages will be log to base 2 of 32 or 5 stages. And one more last step is required, which is essentially something called the bit reversal. The reason for this, as you would have seen, is that when the data comes out of these 5 stages of FFT, it turns out that the order in which it comes is different from the order in which it came out. This would normally, rather than being 0, 1, 2, 3, this would be the 0th value, then the 16th value, then it would be the 8th value, etc., right. If you look at what is happening over there, essentially what will happen is that the value 0, 0, 0, 0 will come out as 0, 0, 0, 0, 1 will come out as 1, 0, 0, 0, right. The index locations are essentially shuffled around. That is a property of this particular architecture, it is not a property of the Fourier transform by itself. It happens because you are using this particular architecture to implement it. Now, this bit reversal can be done in two ways, either you do it at the end or you do it at the beginning before you feed it into the actual stages. If you look at the code over here, you will see that it has actually been done before feeding it into the stages. That is fine, right. The important thing to keep in mind, which in general is a good thing for all of you to keep in mind when you are writing code, is basically to see that how are we structuring the code. We have one function which in turn calls a bunch of other functions. Okay. Broadly, you can think of it as each function becomes a module in Verilog. Okay. So, in some ways writing these functions inside functions is overhead. It is actually introducing lot more modules than are required, but this is the whole principle of hierarchical design. Understanding it and making modifications becomes easy. So, I would strongly recommend you write your code like this. Do not write huge for loops and code that just sort of stretches out at one shot, because it becomes hard to understand, it hard to debug, and especially hard to modify or extend. Okay. If you look at it, this code that we have over here, converting this into a 128 point or a 1024 point FFT is almost trivial, right. Once you look carefully at this and understand what it is doing, making the modifications to this are very simple. More importantly, when we do the synthesis, we will find that it is actually a very useful thing to have done anyway, because it also gives us a better understanding of what is going on. Alright, the FFT 0 block itself is just a for loop that is performing those butterfly computations. Okay. Why is it written in this way? This is pretty much based on the numerical recipes in C code, right, with some adaptations for what is required for getting it properly synthesizable. And this bit reversal function has been implemented in one particular way, which is that what we did is we stored all the indices corresponding to the bit reverse values in an array, right, and what you do is you just look it up. If I have I, the reversed value of I is stored in the array rev underscore 32. I pre-compute that and store it somewhere in a header file. Okay. From a hardware point of view, strictly speaking, this is terribly inefficient, because bit reversal in hardware is an almost trivial operation. It just involves wiring, there is no hardware at all involved, right. But writing the code in C to do that is not so trivial, right. There is a function called reverse in the APFix library which could potentially be used over here. You can experiment with that and try it out, but if you do not have access to such a function, if you write another function that actually, if you try reversing bits in C, you will find that it is actually a very complicated process. Okay. And if you write that code, it just becomes a synthesis nightmare, right, totally not what you want to do at all. So, you use a simpler approach, which is basically you pre-compute the bit reverse values and store them.